Output response of second-order system. The location of poles for second-order system gives an impact to the system output response because every location changes that refer to a pole position will involve changes to the natural frequency omega n and damping ratio zeta. So this can be seen by analyzing the characteristic equation of a second-order system. This one. So from this equation, some conclusion can be made by referring to several cases that are if zeta is greater than 1, both poles will be on the real axis at the different location, like this. If zeta is equal to 1, both poles will be on the real axis at the same location. If zeta if zeta is between 0 and 1, so both poles will be at the location of the complex conjugate on the left half plane. And if zeta is equal to 0, both poles will be on the imaginary axis at different location, like this. All the cases discussed can be illustrated as follows. The shaded area, this one, shows the boundary where poles can be located based on that case. So for case number 1, the system is said to be over damped conditions. Both closed-loop poles can be at any location along the horizontal line here on the left half plane, depending on the gain applied to the system. The system is said to be over damped as long as both poles are at different location from each other. For the second case, this one, the system is under category critically damped condition. So both closed loop poles for critical damping are at the same location like this, which is overlapping on one another. The poles are only located at one position and only involves a fixed gain value. That means the parameters such as settling time, rise time are fixed for the critically damped case. Next, for the third case, the system is said to be in an the system is in an underdamped condition. So in this case, both poles are located at the complex conjugate. So at this area and this area. So the coordinate for the location of the poles for this system is in the form of complex number, which consists of both real and imaginary component. Last one, the fourth case shows a system in an undamped condition whereby both poles are situated on this imaginary axis. So in this situation, the system is constantly oscillate with a constant magnitude each time and is known as marginally stable. This is the response for the 4 cases that I have mentioned just now. So as you can see here, this is the response for the case number 1, overdamped case, which is happen when zeta is greater than 1. So the second one is a critically damped cases, which is case number 2 when zeta is equal to 1. As you can see, both response critically damped and overdamped both look like first order system, which is there is no overshoot involved in this response. So for the next response, this is underdamped case. Underdamped case occurs when zeta is between 0 and 1. So as you can see here, there is overshoot involved in this response. So for the last response, this is we call undamped response, in which this response occurs when zeta is equal to 0. Let us go through one by one. So for overdamped case, for example, we have this response with Cs equal to 9 over S times S squared plus 9S plus 9. Okay, this part we can factorize and then we get this equation. So this function, as you can see here, so there is a pole at the origin that come from unit step input, okay, which is referred to this component 1 over S. So 1 times 9 is 9. So 1 over S here is a input step component. And also have another two real pole, this one and this one, that come from the system. So the input pole, this 1 over S at the origin, generate the constant force response. And these two pole on the real axis generate an exponential natural response whose exponential frequency is equal to the pole location, this one. So that's why we get the result like this. So this component is reflect to the input 1 over S that we inject to the system, and this component is referred to the location of this pole. For critically damped, so for example, we have the response with Cs equal to 9 over S times S squared plus S6 plus 9. Okay, as you can see from this function, there is a pole at the origin that come from the unit step input. So that one is referred to this component 1 over S here. So which is same like overdamped case. Okay. So based on this response also, we have another two pole here that come from the system. 9 over S squared plus 6S plus 9. If we factorize this one, you will get S plus 3 times S plus 3. So that means there is another two pole located at negative 3. Okay. So the pole at the origin generate the constant force response. Okay. And the two poles on the real axis at negative 3 generate a natural response consisting of exponential and an exponential multiplied by time, where the exponential frequency is equal to location of the real pole like this. Okay. Critically damped response are the fastest possible without the overshoot. So means that system without overshoot, okay, only happen for the system with underdamped or overdamped case and critically damped case. Where for critically damped case, that is the response, that is the faster response for the system without overshoot. So this is the result come from this response, where as you can see here, this one is refer to the is reflect to the step input that we inject to the system, and this one is reflect to the location of pole that have we find from factorize this equation. Okay, for underdamped case, let's say we have the response with Cs equal to 9 over S times S squared plus 2S plus 9. Okay, from this function, so there is one pole at the origin that come from the input unit step input. Okay, this is the component for the unit step input 1 over S. Okay, and then also from this function, we can get another two poles here from this function 9 over S power 2 plus 2S plus 9. Okay, after we factorize this function, we will get two complex poles that come from the system. So for second order system, these cases are the common output found in most of the control system, whereby the physical problem of the system itself are among the causes. As you can see here, this is a two pole for the system that located on the complex part. So from this result, we can conclude that an underdamped system yet an exponentially sinusoidal in response to the step input. As you can see from the response of the underdamped cases, so the transient response consists of an exponential decaying amplitude generated by the real part of the system pulse times a sinusoidal waveform generated by the imaginary part of the system pole. So the value of the imaginary part is the actual frequency of the sinusoid known as damped frequency of oscillation or omega t. So the steady state response unit step was generated by the input pole located on the origin. This is the exponential decay generated by real part of complex pole pair, and this one is a sinusoidal oscillation generated by imaginary part of complex pair. For undamped response, so this is same like the previous response where the input pole at the origin generate the constant force response, and the two system poles on the imaginary axis at plus minus J3. This is come from this equation where when we put this one equal to 0, so we get S equal to negative J3 and S equal to positive J3. So this imaginary axis come from this equation will generate a sinusoidal natural response whose frequency is equal to the location of the imaginary poles. So in this situation, the system will constantly oscillate, as you can see here, with a constant magnitude each time and is known as a marginally stable. So the location of pole is located on this j omega axis. Okay, so this result shows that it constantly oscillates due to the absence of a real part in the pole pair correspond to an exponential that does not decay. Generally, all the cases that we have discussed can be simplified as follows. So for undamped case, so zeta is equal to 0. So for this case, the location of pole is on the imaginary axis, which is located at which the location is at plus minus j omega n. Okay. For the critically damped, zeta should be equal to 1 and the location of pole is overlap each other. So there are two pole overlap each other at real axis. So it is equal to negative omega n. So for overdamped case, so zeta should be greater than 1. So in this case, so both pole, which is called S1 and S2, is located on the real axis but different location. So we can use this equation to represent the location of pole for this case. Okay, for the underdamped case, so zeta should be between 0 and 1. So in this case, the location of pole uh, is placed at the complex part. So in order to represent this location of pole, we can use this equation. So this is how we can summarize all this equation in S plane.